Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll introduce the concept of multiple regression analysis. Multiple regression is appropriate for research scenarios when we have two predictor variables and a single continuous outcome variable. For the purposes of this lecture, I'll be explaining situations where we only have two predictor variables. However, multiple regression is appropriate for when we have two or more predictor variables. We can use this framework of multiple regression for when we have any number of multiple predictors predicting a single continuous outcome. Some typical regression applications are as follows, and these research questions are essentially similar to the research questions that I introduced during the video lecture for simple regression, but now we're thinking about adding additional predictors to just the single predictor that we would have investigated before. So the first research question, as an example, might be, do length of time in therapy and therapist rapport influence depression? In this example, the two predictors are time in therapy and the therapist rapport scale. Both would be numeric predictors, and the outcome would be depression, a numeric scale. A second research question might be, do social support and academic self-efficacy influence the stress level of college freshmen? Again, now we have two predictors here, social support and self-efficacy, measured with numeric scales. And we have a continuous numeric scale as an outcome measuring stress. The third research question example might be, do GRE and college GPA predict graduate school GPA? We know that both GRE and GPA are numeric and continuous scales, and our outcome would be grad school GPA, also a numeric and a continuous scale. This is what the multiple regression equation looks like. So you can see that it's an extension of the simple linear regression equation. We are incorporating an additional predictor into the equation, similarly to how we incorporated the first predictor. So now in this equation, beta 0, again, this is the population equation. Note the use of the Greek betas. Beta 0 is the population intercept, and beta 1 and beta 2 are the slope coefficients. So now we're going to have a slightly altered interpretation of the intercept and of the slopes. The interpretation of the intercept beta 0 is now the predicted value of y when all of the predictors are equal to 0. And now the slopes reflect the unique influence of each predictor. So each slope coefficient is representing the predictor to which it corresponds. Now let's move to an example of how we might fit a multiple regression. So if we go back to the example that we looked at with simple linear regression of predicting the cost of a bird scooter, we might not just need the bird scooter to get to where we need to go. We might have to actually split our trip to get to where we need to go between a bird scooter and an Uber. So in order to do this, we would have to account for the time we would spend on the scooter and the time that we spent in the Uber in our prediction of cost. So this is what that equation would look like. The bird has an initial fee of $1, and Uber has an initial fee of $2.10 just to activate the bird or just to initially get into an Uber. And let's say that for the sake of this example, that both modes of transportation are 15 cents per minute thereafter. We can model this in this multiple regression equation. So because we have to use both modes of transportation and we have these initial fees, our new intercept is now going to be 3.1 or $3.10. That's the initial fees added for Bird and Uber. And then because both are 15 cents per minute thereafter, our slope coefficients for each are going to be 0.15 and 0.15. Bird means number of minutes spent on the Bird scooter, and Uber means number of minutes spent in the Uber. So again, now we can substitute values of our predictors, time spent on the bird or time spent in the Uber, into this predicted cost equation. And substituting the scores into the right side of the equation will give us that predicted value on cost or our outcome. However, now because we are thinking about multiple predictors, each combination of predictors will yield a different predicted score on the outcome, in our example, cost. And these values form a three-dimensional regression surface. So let's take a look at this plane. This would be an example regression plane for our cost example. So we can see that now there are 3 axes as opposed to 2. What was the traditional y-axis still has cost on it. That's this vertical axis here. But now there are 2 horizontal axes. There's a horizontal axis for number of minutes spent on bird, and then a horizontal axis that kind of extends out in the opposite direction for the number of minutes spent in the Uber. And this, instead of creating just a 2-dimensional line, because we have to account for this second predictor, we now have a 3-dimensional plane that gives us indicators of the slope for both the minutes spent on the bird and the minutes spent in the Uber as a predicted value of cost. So this is what that plane looks like in general. And then on this plane, we can identify predicted cost. So for example, here, I've highlighted with a point the predicted cost for when we've spent 5 minutes on the bird scooter and 5 minutes in an Uber. The predicted cost would be $4.65. And we can see that that corresponds to cost on the vertical y-axis. So essentially, we have to go on locate on the plane where 5 corresponds to number of minutes spent on the bird and 5 corresponds to number of minutes spent in the Uber. And that point will give us the approximate cost or the predicted cost for 5 minutes spent on each vehicle. So by this point, we've talked about the fact that each predictor has a slope, and these slopes are represented by what we call partial regression coefficients. The slopes reflect the unique influence of one predictor while holding the other predictor constant at any particular value. So essentially, we consider the slopes to be representing the influence of one variable while holding the other variable constant. We also call this controlling for or partialing out the other variable. So let's take a look at these slopes for the time in the Uber and time spent on the bird in this cost example. So again, here is a picture of this regression plane for this example, but now we're looking at it from a different angle. So now we're looking at this regression plane essentially straight on, and we can see that cost now looks more like the traditional y-axis, and that minutes spent on the bird looks more like the traditional y-axis. And then minutes in Uber sort of extends out into the space. I've highlighted here essentially that we can see from this plane that it's angled upwards when we look at cost and minutes spent on the bird scooter. And this shows us that for the relation from minutes on the bird to cost, that we have the same slope at all values of the minutes in the Uber variable. So this plane essentially is flat, right? For the minutes spent in the Uber. It's the exact same slope for the minutes spent on the bird, no matter what value we are at for minutes spent on Uber. Now we can see the same thing for the Uber slope. So again, now we are looking at this plane from a different angle. So we can see, again, the cost vertical axis and the minutes spent on the bird horizontal axis. And now we can kind of see the angle of the slope for minutes spent on the Uber. So we can see that this plane is kind of tilted downwards, angling upwards. It's got a positive slope for minutes spent in an Uber. And that slope is the same slope at all values of minutes spent on a bird scooter. So the slope for Uber, the simple slope, holding bird constant, stays the exact same. So when we hold bird constant, that's essentially saying that for minutes spent in the Uber, the slope relating to the cost outcome, it's going to be the same slope for Uber at all values of bird. This concludes the first lecture on multiple regression. In the next lecture, I'll show an example of multiple regression using the smoking cessation study data.